Welcome to AP Chemistry. In this video, we will build upon the properties of ideal gas behavior and apply them to vapor pressure. That is, the pressure generated by the vapors produced of a substance in the liquid or solid state. Note that the melting point of xenon is about 161 Kelvin and the boiling point is about 165 Kelvin. Do the particles behave as you would expect them to in the simulation provided? Keep an eye on the temperature. Do all the particles have exactly the same kinetic energy? Are all the particles existing in exactly the same state? Notice how close we are to the boiling point. How does the simulation differ from your expectation? Finally, we are now quite past the boiling point, at 500 Kelvin. And yet, do all the particles have exactly the same kinetic energy? What do you think temperature actually measures? On this graph, we have a certain sample of nitrogen gas at different temperatures indicated. Notice how the distribution of those N2 molecules differ from each other at different temperatures. At lower temperatures, the distribution of the velocities of those given particles is much more narrow. However, at higher temperatures, there is a much greater distribution of speeds. We can make a similar relation between different substances. In the previous example, we had displayed the same number of xenon atoms at 500 Kelvin. Now we are viewing 100 particles of helium, the same number, at 500 Kelvin as well. The speeds differ most distinctly. Thus, at one given temperature, a certain number of gas particles will differ in their speed distribution according to the difference in the mass of their particles. Recall that kinetic energy of one particle is equal to 1/2 mv squared, mass times velocity squared. The more massive particles will have a more narrow distribution, while the less massive particles will have a greater distribution of velocities. Therefore, at any given temperature, since temperature measures the average kinetic energy of those particles, there will be a certain portion of particles that have sufficient energy to transition to the gaseous state. These vapors will generate a certain pressure that we can now call vapor pressure. Now, in a closed container, those vapors produced from a given solid or liquid will fill the container up until it reaches its equilibrium vapor pressure, a point at which the vapor pressure will remain constant. This is because as vapors are being generated, there's also the increasing possibility for the reverse process to occur, that is, condensation. Before equilibrium, the rate of vaporization is much greater than the rate of condensation. But as more molecules evaporate, there are more molecules that can now condense, until at equilibrium both rates, the rate of vaporization and the rate of condensation, are exactly equal to each other, and the vapor pressure is maintained. This equilibrium vapor pressure is what is reported as the vapor pressure of a given substance at a given temperature. The vapor pressure is another way, like boiling points, to compare the strengths of intermolecular attractions. However, vapor pressure is inversely related to intermolecular force strength. Thus, diethyl ether shown here, generating the highest vapor pressure, has the lowest intermolecular force strength of the set. When the vapor pressure generated by a liquid or solid at a given temperature meets atmospheric pressure, the substance boils. Boiling points are always, therefore, relative to the pressure of the atmospheric surroundings. If we take the natural log of vapor pressure as a function of the reciprocal of its temperature, we can generate a linear function in order to compare their values. The slope is related to the enthalpy of vaporization for that substance. This linear function is called the Clausius-Clapeyron equation. The more significant the slope is, the higher the enthalpy of vaporization will be. Therefore, the slope is also an indicator of intermolecular bond strength. Rearranging the equations given, we can generate one that relates the vapor pressure at one temperature to the vapor pressure at another temperature for a given substance. At this juncture, we can also refer to phase change diagrams for a given substance. Here, we will use enthalpies of fusion and enthalpies of vaporization, as well as specific heat capacities that relate the amount of heat that a certain substance can hold at a given state. This will allow us to determine the total energy required or released in relation to a given phase transition. Finally, phase diagrams allow us to represent all of the possible states of matter for a given substance in relation to its pressure and temperature. Note that the triple point describes the point at which three phases can exist co-equally, and the critical point is the point beyond which phases do not distinctly exist and determines the supercritical fluid. The essential takeaways of this video relate to the kinetic energy distributions at a given temperature of a given substance, the equilibrium vapor pressure and the Clausius-Clapeyron equation, phase change diagrams, and the application of Q is equal to mc delta T, and phase diagrams at various temperature and pressures for different substances. Till next time, when we consider the mysteries of the absolute, crit.